So we actually solved this one earlier and so that it converges, but we'll do it again. Using the alternating series test. We know our a sub n is equal to 1 over n. The limit of 1 over n as n approaches infinity is 0, so it, remember, past that first one. And your a sub n plus 1, put that a little closer there. Less than or equal to a sub n, where we knew that 1 over n plus 1 is less than or equal to 1 over n. Okay, so we knew it converged. Okay, so now we know it converges. The regular value converges, so we know that converges. So now we have to find out the absolute value of it converges. Okay. Let's say the sum, actually with this one, the sum from n equals 1 to infinity of the absolute value, negative 1 to the n plus 1 over n, which is just equal to, from n equals 1 to infinity, 1 over n. And we know from the p-series test that this is going to diverge. Okay, remember for the p-series, p is less than or equal to 1, diverges. Okay, so we know this one converges, but conditionally. Negative 1 to the n plus 1 over n converges conditionally. Yes.
Is there ever a case where the absolute can converge, but the regular diverges? Or do we not really look at those? Or is that very rare?
I don't remember seeing any where the absolute would converge, but the other one wouldn't. I'm sure there are probably some out there. I just, yeah, I haven't seen it.
There might not be.
It's possible. I haven't seen everything, so. A whole lot I thought I could honestly say, oh, that'll never happen, but. All right, any questions on this one? All right. Oh, anyone's still writing. All right, so let's say, for example, if we wanted to determine each series is convergent or divergent, and if convergent, classify as absolutely or conditionally. Okay, so for problem A, say the sum from n equals 0 to infinity. Uh-oh, clean that up a little bit. Of negative 1 to the nth power times n factorial over 2 to the power of n. And for B, say n equals 0 to infinity of negative 1 to the nth power divided by square root of n. Okay. Now for A, because we have that absolute value there, we're going to kind of start a little bit different. So we're going to use the nth term for divergence. Okay, which is, if you remember, if the limit base of n doesn't equal 0, then the series diverges. Okay, so in this case, I found it was probably easier to show if you just plug in a few values. So if you have the sum from n equals 0 to infinity of -1 to the n times n factorial all over 2 to the power of n, plug in 0, you end up getting 1, minus 1/2 plus 2/4 minus 6 over 8 plus 24 over 16 minus 120 over 32, and it keeps on going like that. Okay, so if we put that on the number line, okay, so let's say we have our 0 here, our 1, our 2, -1, and take it back to -2. Okay. So this is minus 1/2 plus 1/2, so these two just kind of knock each other out. Okay, so right now you're at 1. Minus 6 over 8, which is minus 3/4. So 1 minus 3/4 is 1/4. So you go from 1 to 1/4. Plus 24 over 16, which is reduces to 1 1/2. So you have 1/4 plus 1 1/2 is 7 over 4. So that moves all the way to 7 over 4, which is about right here. Okay. So then it's minus 120 over 32, which reduces to 3 3/4. So 7 over 4 minus 3 3/4 is actually 2. So it goes that way. And then when you plus, it's going to go further. So each way, it goes further and further and further away from 0. So this one actually diverges. As n approaches infinity, the value goes further away, or further. I think it's farther. Is it farther or further? Further? No, I was right the first time. Further away from 0. So it diverges. All right. Any questions on that one? All right. So for B, if we use the alternating series test, clean that G up a little bit. Okay, remember first, the limit of a sub n. So you have the limit of 1 over square root of n as n approaches infinity is equal to 0, so it passes the first one. And the second one, a of n sub of n plus 1 is less than or equal to a sub n, which gives us 1 over the square root of n plus 1, so less than or equal to 1 over square root of n, which is true because this one will always be bigger. Okay? So it passes both conditions. So you know it's convergent. Okay? So now we just have to find out what type of convergent. Okay? So we know that, where is it? I'll circle that. Move this up a little bit. Okay? So we know that if we look at it by the P-series test, you have the n equals 0 to infinity of the absolute value of -1 to the n over, instead of square root of n, we could say n to the 1/2 power, which is equal to the sum from n equals 0 to infinity of 1 over n to the 1/2 power. And we know that diverges, since p is equal to 1/2. So p is equal to 1/2, which is less than or equal to 1. So it diverges. Okay, so this one's conditionally convergent. Okay. Uh-oh. All right, so any questions on that one? All right. Still writing. Oh, yes.
Can you go over why, when p is greater than 0 and less than 1, or greater than or equal to, right? Why that still diverges?
With that one,
It's the negative would just bring it up from the denominator, right?
yep, if it's negative, it just comes up and it increases. But if it's, I'm trying to remember the proof. So if p is, I think we did the equal one.
Anything greater than 1 is
Yep.
convergent, and then 1.
Yep, anything greater than 1, but less than or equal to 1 is divergent.
Yeah, I'm just trying to think of like why.
I think the proof is in, was it last class or the class before that the
I think it requires the integral test be proved.
Yeah, it does.
Okay.
Yeah, but actually was proven, was it last class notes?
That was the 28.
28? Oh, okay. So, yep.
Like a calculator makes it pretty easy to see as well.
Yeah.
I got the 3. So that you think it was. Actually, sorry, the 0 is what we used.
All right, so let's say for our next example, we want to determine whether the sum from n equals 1 to infinity sine of 18n over n to the 10th power converges or diverges. And if it converges,
P is just
what type of converging does it do?
So, yeah, just a different way. Because it also has this condition of continuous positive.
Is it uh-oh,
So there's like
conditional
divergence tests.
or absolute? Conditionally or absolutely?
Sine of 8n.
Hmm?
The 8n with the sine.
Yep, sine of 18n.
18.
Yep, 18. Oh, clean that up a little bit. There we go. Okay, so whenever you have one of these with sine or cosine, you always want to start with that between -1 and 1. Okay, so we know that sine of 18n is between -1 and 1. Okay. So if we divide all three terms by n to the 10th power, we have -1 over n to the 10th power. It's equal to sine of 18n over n to the 10th power. Less than or equal to 1 over n to the 10th power. Okay, so this one, if we get just the absolute value, then we won't have any of these negative values here. So we'll know that the absolute value of sine of 18n over n to the 10th power will be less than or equal to 1 over n to the 10th power. Okay, so we know here the absolute value is going to be less than or equal to 1 over n to the 10th power. Let's say if we make this our a sub n and our b sub n. Okay, so we know if this is always going to be less than our b sub n, and we using the comparison test, the sum of 1 over n to the 10th power, n equals 1 to infinity, converges. Remember, that's for p is greater than 1. Okay, so that means if this one converges, then this is also going to converge. So that means from n equals 1 to infinity, the absolute value of sine of 18n over n to the 10th power also converges. Okay, but this one converges absolutely. All right, so any questions on that one? All right. Leave that up there for a few more seconds. Okay. Oh, are you still writing?
Yeah, I'm fine.
No, okay. Okay, so now we're going to use the ratio test. Okay, so let's say if we let a series, and we'll leave that blank because I don't know if it's starting from 1 or 0. So we'll leave that blank, just the series, or be a series, with non-zero terms. Okay, so 1, that series converges absolutely if the limit of a of n sub n plus 1 over a sub n, as n approaches infinity, is less than 1. We'll clean up that infinity a little bit. There we go. Two, the series diverges if that limit of the absolute value of the ratio of a sub n plus 1 over a sub n is greater than 1 or it equals infinity. So either it's greater than 1 or it doesn't exist. Which, if it's greater than 1, it doesn't necessarily mean it's infinity. Okay. Now the ratio test is inconclusive if the limit of the ratio is equal to 1. That just means you have to use another test. And the proofs will be on the notes when I scan them, so if you want to see those, more than welcome. All right. So let's say, for example, determine if the sum from n equals 0 to infinity, 2 to the nth power over n factorial, converge or diverge. Oh, clean that up a little bit. Okay, so for this one, our a sub n is going to equal 2 to the nth power over n factorial. So that means your a sub n plus 1 is going to equal 2 to the n plus 1 power over n plus 1 factorial. Okay, so that means the limit of the ratio of a sub n plus 1 over a sub n as n approaches infinity is going to equal the limit as n approaches infinity of the absolute value of 2 to the n plus 1 power over n plus 1 factorial divided by 2 to the nth power divided by n factorial. Which means we can just write down our first fraction, change that to multiplication, flip the second one. So the limit as n approaches infinity, 2 to the n plus 1 power over n plus 1 factorial times 2 to the nth power over n factorial. Okay. So here's where you have to do just a little bit of tweaking. Okay. So we can rewrite n plus 1 factorial. We can make that n plus 1 times n factorial. And our 2 to the n plus 1 power can equal 2 to the nth power times 2 to the first power, or just 2. All right, so that's going to equal the limit as n approaches infinity of the absolute value 2 to the n plus 1 power is 2 to the nth power times 2. Our n plus 1 factorial is just n plus 1 times n factorial. times, oh, that one actually should have flipped. Forgot to flip it. I'd say that should have canceled out. So that should be n factorial over 2 to the nth power. Sorry about that. But you can always tell if you forgot to flip it, because if nothing cancels out, you'll know why. 2 to the nth over n factorial. Oh, did I just flip it back? Yes, I did. About to do it again. N factorial over 2 to the nth power. I just flipped it again. Like I said, you always know when you didn't flip it right, because nothing will cancel out. Okay? Because the minute you flip it correctly, the 2n will cancel out, and the n factorial will cancel out. Like I said, if you do that, nothing cancels out, you messed up somewhere. Okay, so this is the limit as n approaches infinity, the absolute value of 2 over n plus 1, which will always be positive, so you don't really need the absolute value anymore. Which is actually equal to 0 as n approaches infinity. Okay, so that is less than 1. So we know it converges by the ratio test. Capitalize that. All right, any questions on that one? Opening up. All right, leave that up for a few more seconds. All right, so for this one, let's say, for example, here, if you wanted to determine if the sum from n equals 0 to infinity n squared times 2 to the n plus 1 power over 3 to the power n converge or diverge. Okay. So our a sub n is going to be n squared times 2 to the n plus 1 over 3 to the nth power. That means our a sub n plus 1 is going to be n plus 1 squared times 2 to the n plus 1 all over 3 to the n plus 1 power.
So you can't just make that n plus 2?
Yep.
Oh, you can? Okay.
Yep.
Sorry.
Oh, no problem. Okay, so that leaves you with n plus 1 squared. That's n plus 1, just 2 to the n plus 2, over 3 to the n plus 1. Okay, just like before, we can always change that. So you have n plus 1 squared times 2 to the n times 2 squared, 3 to the n, well, times 3. Okay, so we have our a sub n and our a sub n plus 1. Okay, so now we have the limit, the absolute value of a sub n